If a gamma ray burst were pointed at Earth right now, you wouldn't see it, you wouldn't feel it, and you wouldn't have time to understand what was happening. One moment the sky would look normal. The next, our atmosphere would be stripped away, the surface sterilized, and every complex organism on the sunlit side of Earth would vanish in seconds. The most terrifying part is that this destruction would come from a beam of light, not a planet-sized object, not a black hole near us, just light focused into the most powerful beam the universe can create. Most people hear deadly space event and think of supernovas, asteroid impacts, or black holes devouring entire stars. But those aren't the universe's most dangerous weapons. The real monster is something far stranger, far more violent, and far more unpredictable. It's a gamma ray burst, a cosmic explosion so powerful that in less than a second, it can release more energy than our sun will generate in its entire 10 billion year lifetime. It is the closest thing our universe has to a natural doomsday switch. A gamma ray burst, or GRB, is the brightest, most energetic flash of electromagnetic radiation known to science. They come in two types, long and short, but both are unimaginably violent. When a massive star collapses into a black hole, its magnetic field and rotation can focus the explosion into twin beams that shoot out of its poles at nearly the speed of light. When those beams are aligned with us, they appear as a gamma ray burst. Shorter bursts come from an even more dramatic source, the merger of two neutron stars, the densest objects in the universe, besides black holes themselves. These collisions release titanic beams of energy, powerful enough to reshape entire regions of galaxies. To understand how extreme a GRB is, imagine every star in the Milky Way flaring simultaneously and still falling short of the energy released by a single burst. Imagine the sun shining as bright as it does for 10 billion years. A gamma ray burst can match that output in 1 second. Nothing else we know of, not black holes, not quasars, not supernovas, unleashes its power as suddenly or as intensely. And yet, despite their destructive potential, GRBs are invisible until the moment they hit. Their beams are incredibly narrow, sometimes only a fraction of a degree wide. If you're inside that beam, you're gone. If you're outside it, you might never know an explosion happened at all. It's like a sniper rifle aimed across the galaxy, firing without warning. But the bullet moves at the speed of light. Right away, you can see why this topic is so misunderstood. Most people assume the universe's biggest killers are large objects or massive explosions, but that's the expectation. The reality is that the universe's deadliest weapon isn't something that crashes into you. It's something you never see coming. A flash of radiation fired from thousands of light years away. Scientists have spent decades studying GRBs, and what they've found is both terrifying and fascinating. These bursts have been detected in distant galaxies billions of light years away, meaning their true energy is beyond anything we can comprehend. Modern satellites, like NASA's Swift and Fermi telescopes, pick up these bursts seconds after they appear, measuring how long they last, how bright they are, and how fast they fade. From this data, we've pieced together the truth of how stars die, how black holes are born, and how entire regions of galaxies can be sterilized in an instant. But the most important question for us is simple. Could this ever happen to Earth? The answer is yes and no. Gamma ray bursts are rare. In a galaxy like ours, they might occur once every 100,000 to a million years, and the beam has to be pointed directly at us to be lethal. But if that alignment ever happens, distance offers little protection. A GRB within 6,000 light-years could destroy Earth's ozone layer completely, letting lethal ultraviolet radiation from the sun reach the surface. Closer bursts could strip the atmosphere, ignite global chemical reactions, and erase the possibility of complex life on the exposed side of the planet. Some scientists even believe a gamma-ray burst may have caused a mass extinction hundreds of millions of years ago. This isn't sensationalism, it's astrophysics. These events are real. They happen constantly across the universe, and they shape the evolution of galaxies, influence where life can form, and may explain why advanced civilizations are so rare. GRBs might be the answer to some of the biggest questions in cosmic biology. Why is life fragile? Why is it rare? Why does it take so long to evolve? A single GRB could reset the biological clock of an entire region of a galaxy. And this is just the beginning. Because as powerful as they are, the story behind GRBs is even more incredible. They reveal how the universe creates black holes, how neutron stars collide, how chemistry is forged in the aftermath of destruction, and how entire galaxies are shaped by bursts of light that last only seconds. In the next 5 parts, you're going to learn exactly what makes a gamma ray burst the deadliest explosion in the universe, how they're created, which stars near us could produce one, how a GRB could wipe out life on Earth, and how these events may be one of the biggest reasons we haven't found intelligent life anywhere else. You're also going to see why the universe may be far more hostile than we ever imagined, and why, despite all that danger, we are incredibly lucky to exist right now, in this moment, in this tiny safe pocket of the Milky Way. And by the time you hear the full story, you'll understand why scientists call gamma-ray bursts the universe's ultimate kill shot, and why the deadliest force known to science isn't a planet, a star, or a black hole. It's a beam of light. To understand why gamma-ray bursts are the most dangerous events in the universe, you first need to understand their anatomy. A GRB is not just an explosion. It is a precision-engineered cosmic weapon created by extreme physics that occur only in the final moments of a star's life or during the most violent collisions in the cosmos. Unlike supernovas, which explode in all directions, GRBs focus nearly all their energy into 2 razor-thin beams. Those beams are so narrow that if you stood slightly off to the side, you'd survive. But if you're in the direct line of fire, no distance is truly safe. There are 2 main kinds of GRBs, and each one is more violent than almost anything else the universe produces. The first are long-duration gamma-ray bursts, which can last from 2 seconds up to several minutes. These are created when a massive star, 12 of times heavier than the Sun, runs out of nuclear fuel. When that happens, the star can no longer support its own weight. Gravity wins. The core collapses inward at 1/4 of the speed of light, forming a black hole within seconds. But the collapse doesn't simply end with the star disappearing. As the black hole forms, the outer layers of the star fall inward, collide, and begin spiraling around the newborn singularity. This fast-moving material forms an accretion disk hotter than anything else in the universe. The star's magnetic field, twisted and amplified by the collapse, forces some of this material to escape through the poles. Instead of forming a spherical blast, the energy is funneled into 2 narrow jets that punch through the star's outer layers like drills. When those jets break free into space, they release a gamma-ray burst. This kind of event is called a collapsar or hypernova. It is the most powerful type of stellar death known to science. A single long-duration GRB can release more energy in 10 seconds than all the stars in the Milky Way combined emit in the same amount of time. It is the ultimate ending for a massive star, a transformation into a black hole, accompanied by a burst of radiation capable of sterilizing planets thousands of light years away. The second kind of gamma-ray burst is short duration, lasting less than 2 seconds. But these bursts are even more violent in terms of what creates them. Short GRBs occur when two neutron stars, each one a city-sized object with more mass than the Sun, spiral into each other and collide. These neutron stars are remnants of previous supernovas, made almost entirely of neutrons packed together so tightly that a single teaspoon of their material weighs billions of tons. When two of them crash together, their incredible density and gravitational energy create an explosion powerful enough to shake the fabric of space-time itself. This collision not only produces a burst of gamma radiation, but also forges the universe's heaviest elements: gold, platinum, uranium, materials that require energies impossible to achieve anywhere else. The merger then collapses into a black hole, and once again, the magnetic fields channel the remaining material into thin beams that shoot outward as a short gamma-ray burst. Even though a short burst lasts only milliseconds to seconds, its energy output can exceed anything humans can compare it to. It's like taking the force of every nuclear bomb ever built, multiplying it billions of times, and firing it through a cosmic laser pointer. But the most important part of this anatomy is the beam itself. Unlike ordinary explosions, GRBs are directional. Their beams are extremely narrow, often only a degree or less in width. To visualize how tight that is, imagine standing in front of a flashlight from thousands of miles away. If the flashlight beam were as narrow as a GRB, stepping just a few feet to the side would take you out of the danger zone. But if you're inside it, the full force of the burst hits you head-on. This razor-thin targeting is what makes gamma-ray bursts uniquely dangerous. A supernova that explodes in all directions loses energy quickly as it spreads out. A GRB, however, packs nearly all its power into a focused line, increasing the intensity by orders of magnitude. This means that even at vast cosmic distances, thousands of light-years away, the beam can still deliver enough energy to strip away atmospheres or disrupt biological chemistry on planets unlucky enough to be in its path. Nothing else in the universe combines this level of focus with this level of power. Why does the universe create such narrow beams? The answer lies in angular momentum and magnetic fields. When a collapsing star or merging neutron stars begin spinning faster during the final moments of their lives, conservation of angular momentum forces them into extreme rotation. The magnetic fields amplify, channeling material along the poles. These beams are the universe's natural exhaust system for releasing rotational energy. They form because the core can't explode uniformly. Instead, the blast takes the path of least resistance, straight out of the poles, forming twin cosmic jets that carry astonishing amounts of energy along a single line. Understanding this anatomy matters for a simple reason. It determines who lives and who dies. A GRB is not a gentle glow spreading across space. It is a weapon with a barrel. It fires in a straight line, and anything in that line experiences the full force of the explosion. Astronomers estimate that if a GRB were pointed directly at Earth from within a few thousand light-years, the consequences would be catastrophic. But if the burst was angled just a bit away from us, we might detect it as a flash in distant space, completely harmless. This directional nature also explains why GRBs are rare but devastating. Millions of GRBs have happened across cosmic history, but only a tiny fraction of planets were ever in their beams. It's a cosmic lottery, one you never want to win. And yet, despite how deadly gamma-ray bursts already are, this entire anatomy still doesn't reveal the full danger, because the real threat isn't the explosion itself. The real danger is what happens to a planet when that beam actually hits. And what follows is far more frightening than the burst alone. To understand why gamma-ray bursts are considered the universe's ultimate kill shot, you have to imagine what happens when that razor-thin beam of radiation actually reaches a living world. The burst itself lasts only seconds, but the damage it inflicts unfolds over hours, days, and centuries. It isn't a dramatic, cinematic explosion. It's something far worse, an invisible transformation of a planet's atmosphere into a weapon against every living thing on its surface. When a gamma-ray burst strikes a planet like Earth, the first thing it does is slam the atmosphere with high-energy gamma photons that break apart molecules on contact. Oxygen and nitrogen, normally harmless and essential for life, are ripped into fragments. Those fragments recombine into toxic compounds, such as nitrogen dioxide. This single chemical reaction can turn the entire upper atmosphere into a brown haze that blocks sunlight, cools the planet, and floods the surface with damaging ultraviolet radiation. But the most devastating effect is what happens to the ozone layer. A GRB can destroy it completely within minutes. Without ozone to absorb solar ultraviolet light, the surface becomes a hostile environment where DNA breaks apart faster than life can repair itself. Plants die first. Phytoplankton in the oceans, which produce most of the oxygen we breathe, collapse. Food chains unravel, the oceans darken, the land follows. Within weeks, entire ecosystems can collapse from nothing more than the sun's ordinary radiation, now unfiltered and lethal. This is not speculation. These reactions have been modeled in detailed atmospheric simulations. A gamma-ray burst within a few thousand light-years could cause a 30% drop in ozone globally, and a far greater drop on the side of the planet directly facing the beam. Even a moderate burst could subject the surface to UV levels 10 times higher than anything life on Earth has ever evolved to survive. Anything caught in sunlight, plants, animals, even microbial layers on soil would be sterilized. Night would offer temporary protection, but only until atmospheric circulation carried the damaged air around the globe. And the damage doesn't stop with radiation. A GRB striking Earth would produce nitrogen dioxide in such quantities that the sky would darken to a reddish-brown color for months. That toxic haze would block enough sunlight to cool the climate significantly. Temperature drops triggered by ozone destruction could spark global freezing events, disrupt rainfall, create droughts, trigger mass die-offs, and push ecosystems into collapse long after the initial radiation surge passed. A planet hit by a GRB doesn't just suffer a moment of destruction, it enters a long, drawn-out environmental spiral that can last years or even thousands of years. This chain reaction is so dramatic that scientists believe at least one mass extinction in Earth's past may have been caused by a gamma-ray burst. Around 450 million years ago, during the late Ordovician period, nearly 85% of marine species died out in one of the most severe extinction events in our planet's history. There is evidence that the extinction began suddenly, with intense ultraviolet radiation damaging surface-level organisms, followed by rapid global cooling. These signatures match what we would expect from a GRB striking Earth. While the exact cause is still debated, the possibility alone shows how devastating these events can be and how they shape the evolution of life. The lethal radius of a GRB is enormous. A burst within 500 light-years could obliterate the ozone layer completely. A burst within 1,000 to 2,000 light-years could cause mass extinctions. Even at distances of 5,000 to 6,000 light-years, The radiation could cause measurable chemical changes in the atmosphere. For context, the diameter of the Milky Way is about 100,000 light-years. This means a single GRB can threaten life across vast regions of the galaxy. It is the only known natural phenomenon capable of sterilizing not just planets, but entire stretches of spiral arms. And unlike supernovas, GRBs don't need to be close to be dangerous. They don't lose energy by spreading outward in all directions. Their beams concentrate power like a cosmic cutting laser. This is why they can erase a biosphere from thousands of light-years away. Even if the beam only hits one hemisphere, the long-term atmospheric damage would eventually circle the globe. A civilization could vanish without its planet ever being physically touched. No debris, no impact crater, no warning. Just a sudden, irreversible collapse of the atmosphere's protective layers. If a human civilization existed on a planet hit directly by a GRB, it wouldn't have time to respond. Satellites would fail instantly. Communications would collapse. Electronics would burn out. Anyone outdoors would be exposed to lethal radiation. Crops would die within days. Oceans would begin losing the life that produces oxygen. Even underground shelters couldn't protect a society from the long-term atmospheric transformation. A planet that spent billions of years nurturing life could lose everything in a burst, lasting less than the time it takes to boil water. This mechanism may explain why advanced civilizations are so rare in the galaxy. Life requires billions of years to evolve complexity, but GRBs can reset that progress instantly. They may act as a cosmic filter, an invisible hazard that periodically wipes out regions of the Milky Way, preventing life from reaching higher intelligence before starting over again. In this light, the existence of humanity is even more remarkable. We live on a world that has avoided alignment with any recent GRB, allowing life to evolve steadily for hundreds of millions of years. But this safety isn't permanent. The Milky Way contains many stars capable of producing gamma-ray bursts. Most are far away and unlikely to be aligned with us, but not all. There are known massive stars in our region of the galaxy that could produce collapsers, and there are neutron stars orbiting each other on decay trajectories that will one day merge. Both long and short GRBs continue to occur across the universe, and although the odds are small, Earth is not immune. We've explored how a GRB kills a planet. We've traced the chemical catastrophes, the atmospheric collapse, and the way entire biospheres can disappear without a single physical impact. But all of that raises a far more unsettling question, one that shifts this from cosmic curiosity to personal relevance. We know what GRBs can do. We know how far their reach extends. The real question is simple. What if the most dangerous one is aimed at us? If gamma-ray bursts are the universe's ultimate kill shot, then the next question becomes painfully obvious. Where is the gun pointed? The Milky Way contains hundreds of billions of stars, but only a rare few can produce a GRB. Those few, however, are powerful enough to reshape the future of life in our galaxy. Some of them are safely distant. Others are dangerously closer than we'd like. And at least one has fueled years of debate about whether Earth might be directly in its line of fire. The star that has attracted the most fear is Wolf-Rayet 104, a massive, stripped-down stellar core located about 8,000 light-years away in the constellation Sagittarius. Wolf-Rayet stars are some of the most extreme objects in the universe. Hot, massive, and losing their outer layers at incredible speed. They are the final stage before a massive star collapses into a black hole. And WR-104 isn't just any Wolf-Rayet star. It sits inside a beautiful spiraling pinwheel nebula formed by winds colliding between it and its companion star. But beauty hides danger. Wolf-Rayet stars are prime candidates for long-duration GRBs because their stripped hydrogen layers allow jets to escape more easily during collapse. For years, WR-104 captured the public imagination because early observations suggested a frightening possibility. The spiral pattern surrounding the star appeared almost face-on from our perspective, implying that we might be looking directly down the barrel of a future GRB. If the star's rotation axis aligns even slightly toward us, a collapse could send a gamma-ray burst straight at Earth. Scientists later refined these measurements and concluded that perfect alignment is unlikely, but not impossible. And when the stakes are this high, unlikely is never fully comforting. WR-104 is not the only dangerous star. Several other massive stars in the Milky Way could produce GRBs when they die. Some reside in dense clusters near the galactic center. Others orbit in isolated pockets in our galaxy's spiral arms. The common factor is mass. Stars at least 20 to 30 times the mass of the Sun. Many of them are losing mass rapidly or rotating at extreme speeds. Both are necessary ingredients for a GRB. These stars sit like ticking clocks with timelines measured in hundreds of thousands or millions of years. Their deaths are guaranteed. The only question is whether their beams will point at us. Then there are neutron star binaries, pairs of dead, ultra-dense stars locked in orbits that slowly decay as they lose energy through gravitational waves. Eventually, they spiral inward and collide, producing short gamma-ray bursts. These systems are much harder to detect. Some are known, but many remain invisible until they merge. And because short GRBs are even more focused than long ones, their beams can be deadly from great distances. The Milky Way likely contains dozens of binary neutron star systems on collision courses that we cannot currently see. The most important factor is alignment. With GRBs, distance alone doesn't decide danger. A burst 20,000 light-years away but aimed at Earth is far more dangerous than one 2,000 light-years away that is angled slightly away from us. This is what makes GRBs such eerie cosmic threats. You can have a massive star practically next door and be completely safe, or a star on the opposite side of the galaxy that ends life on your planet if its jet happens to be pointed in your direction. Astronomers use several techniques to measure alignment. They study the shape of stellar winds, the geometry of surrounding nebulae, the rotation of star surfaces, and the oscillation of spectral lines. They also track precessional wobbling, small shifts in the orientation of a star's axis over time. But even with these tools, predicting a GRB is incredibly difficult. We can estimate risk. We can identify candidates, but we cannot look at a star and say with certainty that its death will or will not produce a jet pointed toward us. And then there's the timeline problem. Massive stars live fast and die young, but young still means millions of years. Astronomers cannot tell whether a dangerous star will explode tomorrow or in a million years. From a human perspective, that timeline feels distant, but from a galactic perspective, it's the blink of an eye. Life evolves slowly. Extinctions happen instantly. The only reason Earth has had the luxury of stability for so long is because no dangerous GRB happened to be aimed at us during the critical windows of evolution. The future offers no such guarantees. So, what are the odds? Statistically, the probability of Earth being hit directly by a GRB in any given million-year period is small. But small does not mean zero. Considering the number of massive stars, the number of neutron star binaries, and the number of bursts that occur across cosmic time, the cumulative risk becomes real. Life has existed on Earth for roughly 4 billion years. Over that time frame, it is entirely plausible that at least one gamma-ray burst has struck our planet. The Ordovician extinction may be evidence of this. Even if that particular event wasn't caused by a GRB, the physics show that it could have been. The truth is that GRBs don't care about survival, evolution, or intelligence. They simply release energy when massive objects collapse. Any planet in the way becomes collateral damage. Earth has been extraordinarily lucky so far. But luck is not protection. The universe fires these beams at random directions, and over billions of years, almost every region of the galaxy has been swept by them at some point. We just haven't been in the wrong place at the wrong time. Yet. This is why gamma-ray bursts are more than just fascinating scientific events. They are existential reminders of how small we are and how fragile our planet is. Every breath we take, every life form that evolved here, and every civilization that has risen from the dust has done so because our region of space has remained quiet for millions of years. That calm is unusual. It is precious, and it may not last forever. Knowing the threats helps us understand our place in the galaxy. Knowing that stars like WR 104 and merging neutron stars exist reminds us that cosmic danger is always present, even when the night sky looks peaceful. The beam of a GRB doesn't need to cross entire galaxies to cause damage. It only needs alignment. A firing angle measured in fractions of a degree can decide the fate of life on a distant world. But even these stars, with all their destructive potential, are only the beginning. They are not the largest forces shaping the galaxy. They are not the deepest dangers lurking in the cosmic dark. Because behind every GRB, behind every blast of radiation and every collapsing star, is another story. A story older, larger, and far more violent. And compared to what comes next, even these monsters are small players. Gamma-ray bursts aren't just threats to individual planets. Their influence stretches across the architecture of galaxies themselves. When astronomers look at the distribution of galaxies, where stars form, where planets can survive, and where life might emerge, one pattern appears repeatedly. Violence shapes everything, and GRB are part of the deepest, oldest violence in the cosmos. They have sculpted the Milky Way for billions of years, deciding which regions flourish with stars and which remain barren. In some ways, GRBs are the invisible hands guiding the evolution of galaxies. One of the first clues comes from how galaxies stop forming stars. Star formation requires cold gas, vast clouds that collapse under gravity. But gamma-ray bursts unleash so much energy that they can heat and ionize gas across huge distances, preventing it from condensing. In young galaxies, where massive stars were far more common, GRBs may have regularly swept through star-forming regions, turning cold gas into thin, hot plasma. That plasma cannot collapse, and without collapse, no new stars form. Entire spiral arms could have been sterilized of starbirth by a single burst. Even today, GRBs still influence galactic evolution. When scientists observe regions with unusually low rates of star formation, they often find signatures of past high-energy events, massive supernovas or GRBs that blasted the surrounding gas apart. In this sense, GRBs don't just kill life. They kill the possibility of stars and planets forming at all. They set boundaries for which areas of the galaxy can grow and which remain empty, like scorched patches in a cosmic forest. This destruction leads to an even more important idea. GRBs may determine where civilizations can evolve. Life requires time, vast amounts of stable, unbroken time. It took Earth more than 3 billion years to build complex organisms. Human-level intelligence required even longer, but a GRB can reset that clock instantly. A planet may spend 1 billion years nurturing life, only for a burst to sterilize its surface and force evolution to start again from simple microbes. And this doesn't just happen to one world. A GRB can sterilize an entire region of a galaxy, wiping out multiple planetary systems at once. This realization ties directly into one of the most haunting ideas in modern astrobiology, the Fermi paradox. If the universe is so big and so old, and planets are so common, why don't we see signs of intelligent life? One possible answer is that civilizations almost never get the chance to evolve. GRBs could be the reason. These bursts may sweep through certain regions of galaxies frequently enough to prevent advanced life from stabilizing. Civilizations might begin to develop only to be extinguished before they ever reach the stage of interstellar communication. This is where the dark forest idea becomes even darker. In the dark forest hypothesis, civilizations hide because they fear being destroyed by others. But what if the universe itself is the hunter? GRBs behave exactly like a cosmic predator. Silent, unpredictable, lethal, striking without warning. They erase entire habitats without ever detecting who lives there. They don't need to aim. They don't need intention. Randomness alone is enough to scatter extinction across the galaxy. Perhaps civilizations are rare, not because they hide, but because they are wiped out long before they become visible. Consider what happens in regions near the galactic center. The density of massive stars is much higher there. Massive stars are the primary producers of long-duration GRBs. More massive stars mean more collapsers. More collapsers mean more bursts. The inner galaxy may be too dangerous for complex life to survive for long. Meanwhile, the outer galaxy may be too sparse in heavy elements to form Earth-like planets. That leaves a thin band, just one region, where the balance is right. Not too much danger, not too little metal. A place where life has just enough time to evolve without being reset. This region is sometimes called the galactic habitable zone, and Earth sits inside it. This is not luck, it is survival. The Milky Way is full of areas that may appear calm, but have histories marked by bursts that sterilize their surroundings. Simulations show that in the early universe, when galaxies were young and massive stars were common, GRBs must have been so frequent that they struck the same region multiple times every few hundred million years. That pace of destruction would make it almost impossible for intelligent life to develop anywhere. Worlds would start over repeatedly, never getting the chance to stabilize. The fact that we exist suggests that our section of the galaxy has avoided direct GRB hits for long enough to let evolution proceed undisturbed. The last major mass extinction on Earth happened 66 million years ago from an asteroid impact, not a GRB. Before that, the Ordovician extinction may have been triggered by a burst, but if so, it was distant enough that life eventually recovered. That recovery window, tens or hundreds of millions of years, is something only a stable region can provide. Now zoom out even further. GRB don't just sterilize planets or shape star formation. They influence chemistry across the universe. Their afterglows forge heavy elements. Their shock waves spread metals across galaxies. Their beams can ionize gas across intergalactic space. They may even regulate the growth of galaxy clusters. In a strange way, they are both creators and destroyers, sparking the formation of new elements while wiping out the life that could use them. Violence governs the largest structures of the cosmos. Gravity builds galaxies, but gamma-ray bursts help sculpt them. Radiation carves boundaries. Stars live, explode, create heavy elements, collapse, and fire off bursts that reshape everything around them. And somewhere in that vast, chaotic cycle, life tries to find a foothold. And yet, despite all this destruction, despite the lethal beams and the reset buttons scattered throughout the galaxy, the universe has one final twist. A twist stranger and more beautiful than any explosion, more mysterious than any beam of radiation, and more connected to us than anything else we've seen so far. After everything we've explored, the collapsing giants, the merging neutron stars, the beams of radiation that can erase a world in seconds, one truth rises above all of it. The universe is far more violent, far more unpredictable, and far more fragile than it appears when we look up at the night sky. Gamma-ray bursts are reminders of that violence. They are the universe's brightest flashes and its deadliest moments, bursts of energy that have shaped galaxies, regulated star formation, erased life, and sculpted the cosmic landscape long before our planet even existed. And yet, despite all this destruction, here we are, a species made of stardust, thinking about these forces, studying them, trying to understand them. That alone is astonishing. We've learned that GRBs are not random explosions, but precision-focused beams created in the final moments of massive stars or in the catastrophic collision of neutron stars. We've seen how a single burst can release more energy in one heartbeat than the sun will release over its entire life. We've explored how these beams can strip away atmospheres, destroy ozone layers, alter climates, and sterilize entire hemispheres of a planet without ever touching its surface. We've seen evidence that at least one ancient extinction on Earth may have been triggered by such a burst. We've learned how GRBs influence the structure of the Milky Way, shutting down star formation, disrupting gas clouds, marking out invisible boundaries between safe regions and deadly ones. They may be one of the cosmic filters that prevent civilizations from rising everywhere. If life requires billions of years of stability to evolve, then GRBs may be the reason intelligence is rare, the reason advanced species could be scattered thinly across the galaxy, separated not by distance, but by survival. We've looked at the stars we fear, Wolf-Rayet 104, massive stellar ticking clocks, and merging neutron stars that hide in the darkness until the moment of collision. We've seen how alignment matters more than distance, how a burst thousands of light years away can still devastate any world unlucky enough to lie directly in its beam. We've seen how the probability is low but not zero, and how the history of life on Earth may already bear the marks of one such event. And through all of this, one idea stands out above everything else. We are alive because of where we are. We exist in a narrow band of our galaxy, where star formation is moderate, where heavy elements are abundant, but massive stars are rare, where the last major GRB to sweep this part of the Milky Way occurred long before humans ever evolved. We live inside a quiet pocket of a violent galaxy, a rare safe zone carved out by cosmic chance. Earth has been orbiting the sun for billions of years, and during that time, the universe has unleashed constant waves of destruction. Stars have died in violent explosions. Black holes have formed. Gamma-ray bursts have fired across the galaxy like cosmic sniper shots. Hypernovas have torn apart star clusters. Yet Earth has survived in a window of calm long enough for oceans to form, for life to evolve, for intelligence to rise, and for civilizations to build telescopes capable of seeing these dangers. This is the reality that exceeds expectations. You came into this story expecting a dangerous star, a violent cosmic burst, but the truth is much larger. Gamma-ray bursts aren't just deadly events. They are forces that shape galaxies. They sculpt the conditions necessary for life. They create the heavy elements needed for planets and organisms, and they destroy countless worlds before those worlds ever have a chance to dream. The universe is not gentle. It is not safe. It is an engine of creation wrapped in a cloak of destruction. And yet, somehow, in one small corner of one spiral arm of one galaxy, on a fragile blue planet orbiting an ordinary star, life survived long enough to look outward and notice. Light is the reason we can see the universe at all. It travels across millions of years to reach our eyes, carrying with it the story of suns, nebulae, galaxies, and ancient cosmic events. But light is also the universe's sharpest blade. A gamma-ray burst is light, weaponized, pure energy capable of ending civilizations long before they even know they exist. And yet, we have the ability to understand it, to measure it, to predict it, to fear it, and admire it at the same time. That ability is its own miracle. The atoms in our brains were forged in the same kinds of explosions that create gamma-ray bursts. The iron in our blood was once inside a star that died long before the Earth formed. The calcium in our bones was created by nuclear reactions in ancient stellar cores. We carry the history of the universe inside us. Maybe that is why understanding these deadly bursts feels so profound. We are the result of cosmic catastrophe, shaped by billions of years of destruction that made life possible. We are living proof that even in a universe filled with danger, survival is possible. Meaning is possible. Curiosity is possible. So when you think about gamma-ray bursts, about the beams of light that can erase worlds, remember this: the universe does not care about life, but life still emerged. The universe destroys without intention, but life still persists. And in all the vastness of space, in all the chaos and fire and radiation, we are here asking questions about the very forces that could one day end us. That is the real twist. Not that the universe is dangerous, but that the universe is understandable. That we can witness its violence, map its patterns, and still feel wonder instead of fear. In a universe where light itself can kill, the miracle isn't that gamma-ray bursts exist. The miracle is that we're here to study them.